Now we go on to the next different thing. The lab has developed its teaching consistently over the decades, and there have always been the two sides. Ever since the main effect of the EDSAC was to provide machines for real people to use, there's been what you might call the extra-departmental task of telling the world how to use computers, but increasingly there's the intra-departmental task of passing on to students the models, design principles, techniques and so on that constitute computer science itself. Frank King, I believe, was appointed by Maurice Wilkes in 1969 as a demonstrator, with some brief to lead on the teaching front. Well, Frank took that seriously, and for the last 30 years he's actually been doing that and still doing it with gusto. So it's rather an honor to introduce somebody who's done it for such a long time and to such great effect, as I'm sure many people here realize they were students of, if not Frank himself, but at least on courses that Frank had organized. Frank King.
Well, you don't have to think about the teaching of computing for very long to appreciate that at least two factors make it quite different from teaching most other subjects in the Cambridge portfolio. There is the incredibly fast pace of technological change, and there is the existence of users. Now, the fast pace of change means that you can give a course on a shiny new topic one year, and when you dust it off to repeat it the following year, you're grumbled at for teaching obsolete material. Now, this is invariably the case if your topic exploits the products of a well-known software company. There have certainly been times when I have envied those who give lectures on, say, the annals of Tacitus, when surely one decently prepared course can serve you an entire career. In truth, this approach is not wholly unknown in the teaching of computer science. For example, my own Fortran course lasted a quite indecently long time. Now, users and their needs have been important to the laboratory since its foundation. Indeed, since before its foundation. It was precisely because the university appreciated that many of its members wanted access to the latest computational kit of the day, that the mathematical laboratory was set up in 1937. So the laboratory was undoubtedly giving some form of instruction to users many years before it had any full-time taught course students of its own. Well, with these thoughts in mind, I thought I would indulge, and remembering that we're indulging in a little nostalgia, I thought I would trace a few teaching threads that have run through the department over the years. Now, I shall attempt to avoid the traditional approach of presenting history as a list of date-event pairs, but equally I shall avoid anything trendy, so I shall not be inviting you to empathize with David Wheeler when he was inventing subroutines. So instead, I shall borrow an idea from the earth scientists who tend not to use dates, but relate events to the geological column. So if you ask when something happened, you'll get a reply of the form, "Oh, yes, I remember that well. That happened in the Upper Cretaceous." Well, here is my equivalent, which is this is a computational column appropriate to our local context, and it shows the main platforms that have been used by typical Cambridge users over the years. And I've designated the computers and systems with the names most commonly used at the times that they were up and running. And I've included just two dates, 1949 and 1999, but I have time running linearly downwards, so if you want to have a precise date, you can do your own interpolation. Now, I appreciate that earth scientists would say this whole column was the wrong way up, but of course they would also talk about upper and lower EDSAC, And here I'm on to a winner, because those of you who remember the brief period when these two machines coexisted will know that their relative juxtaposition was as I have them here, with EDSAC 1 on top of EDSAC 2. Now, of course, primitive forms of computational life existed well before 1949. And the pictures which we have been seeing of the early days of the laboratory have prompted me to dig out what one might call a Precambrian view of the new museum site. This is the view in 1815, and these two elegantly dressed Georgian ladies are strolling around somewhere in this very room, near here. Now, my excuse for using this picture is that it shows the site as it was in the time of Charles Babbage, a friend of Maurice Wilkes. And of course, this lecture room is named after him, which is something which has always mildly amused me, because to first approximation, Babbage did no lecturing at all. Now, computational life, of course, evolved somewhat between Babbage's time and the foundation of the mathematical laboratory, but we're here to celebrate the emergence of intelligent computational life. So the earliest entry in my column is the EDSAC. Now, the column continues pretty straightforwardly with EDSAC 2, Titan, and the IBM 370, but after that, my column could get rather messy. You see, by about here, the university had actually run to rather more than one computer. Moreover, the department had split into two parts. But I'm going to keep things fairly simple. The lower half of my column is dominated by Phoenix, which was not a computer, but the name given by the computing service to the system which rose from the ashes of Titan and was implemented on a succession of IBM mainframes. Now, I was a Phoenix enthusiast, but it suffered from a serious defect. The name was terribly difficult for many people to spell. But you can at least pronounce it, which is more than you can say of its successor, the PWF. Actually, Welsh speakers in the audience will They will, of course, tell us that PWF is perfectly pronounceable and sounds very like the word poof. You see, in this cryptic way, the computing service is telling us what it really thinks about the Microsoft products which constitute a public workstation, a facility. Well, now that I have a timescale, I can ornament it in various ways. And let's first look at the in-house teaching provided by the laboratory for its own full-time taught course students. Now, as you all know, the diploma course was given for the first time in 1953 in the early EDSAC era. And for 17 years, this was the only course for full-time taught course students. In 1970, we introduced our first Tripos, a one-year course which still exists today, but it's currently called Part 2 General. Now, to begin with, this was an option of the Natural Sciences Tripos. But sharing a bed with the natural scientists wasn't terribly satisfactory. The principal problem was that our partners felt that we practiced an unnatural kind of science. So the relationship lasted only 1 year, and we've had our own regulations ever since. The 2-year Tripos was introduced in 1978, and that was a kind of stopgap which paved the way for the 3-year Tripos, which is what you might call the real thing, which was begun in 1989. Now, this was a particularly significant moment, because thereby computer science became an admission subject, and in consequence colleges suddenly took an interest in appointing teaching fellows in the subject. The current class of diploma students is now the 46th in the series, and there is every hope that it will run at least to a 50th class, but there are clouds on the horizon because our principal funding body favours modular courses linked to the perceived training requirements of industry, and the diploma course is based on a sufficiently different model that it may succumb. Well, my second thread relates to the extra-departmental teaching. And for roughly the first third of my column, the clients were almost exclusively people engaged in research in other departments. There were academic staff and a few research students, but practically no undergraduates, and there was very little formal teaching. In 1937, the closest approximation to visiting a help desk would have been to pay a call on the young Maurice Wilkes. Now, you could, of course, always consult your fellow users, and this probably is still the main way of getting computing problems sorted out, or becoming more confused than you already were, depending how you look at it. Well, my own early recollection of the kind of user whom I might refer to as a proto-anorak is that such users consumed copious quantities of beer. And in retrospect, I assume that they were being funded in this activity by lesser mortals who were desperate to have their EDSAC programs debugged. And I'm going to refer to this kind of user education as hand-to-mouth, sort of in this sense. Now, the advent of a diploma course did mean that at last there was some formal teaching, and ordinary users quickly saw the advantage of attending selected diploma lectures. And this very much had the blessing of a department, and still does. To this day, the computer laboratory entry in the lecture list reporter is heralded by a rubric which includes the clause, graduates of a university who are not reading for any university examination may attend without payment any lecture proposed by the Computer Science Syndicate. And I will call this form of user education squatting. And this is how I started myself, by attending the opening lecture course in the diploma in 1964. David Hartley gave the lectures and also ran the practical classes. Now, I know that we are here celebrating that it is 50 years since EDSAC ran its first program. But I am here celebrating that it is 35 years since I ran my first program. And I still have the paper tape. And naturally, the program was written in Hartley autocode. Well, by the middle of the Titan era, giving just one course a year suitable for beginners was felt to be somewhat inadequate, but the idea of giving a course more than once a year wasn't a prospect that too many people relished. And David Hartley solved the problem by recording the lectures on an early form of tape recorder, video tape recorder. And this was the first television-based course to be given in Cambridge, and the language he taught was Fortran. And this course marked the start of the mass teaching of users in general and undergraduates in particular. And I joined David Hartley in 1969, and when he became director of the newly formed computing service the following year, a rough division of labour left me teaching the undergraduates and the computing service teaching other users. Now, I couldn't unearth any relics of the Hartley television course, but I have a shot of a slightly later version of the course. This is a Fortran course which I made, and here you see a class attending this course running in the Hopkinson room in the mid-1970s. And if there's anyone here from estate management, you might note that the doors of this room still don't shut properly. Now, as an interesting digression, in 1971, Maurice Wilkes asked me to run a course for members of arts faculties. And the outcome was not only the first course to be given for arts people, but it was the first extra-departmental course to use the Titan multiple access system. Students actually worked online while I explained what to do. Now, at the outset, I said that the teaching of computing has been conditioned by the rapid pace of change. I omitted to say that this rapid pace has at times been backwards. The early television-based Fortran courses assumed that all programs would be prepared on paper tape and later on punched cards, and they made no reference to online computing. The online arts course was a local high point in user education because Titan was on its way out, and we were told that the new IBM computer would not run to an online system. So for a few more years, punched cards were the way of life for the ordinary user. The saving grace, though, was that we developed a cafeteria system which made using punched cards almost bearable. Now, just in case any of you need reminding how the cafeteria system functioned, I'll show a sequence of slides illustrating how I used this facility myself. Now, like an internal combustion engine, the cafeteria system involves a 4-step cycle. First, you sit at a table writing a program, and then you visit the card punch room and punch out the cards, and then you feed these cards into a card reader, and finally you walk over to the line printer waiting for your output to appear, and it helped if you could read upside down. This completes one cycle. You then take the output back to the table, you wonder why the program didn't work, and then you start all over again. Now, fortunately, the computer board got the extra departmental teaching off the punch card hook by funding a project to provide a teaching system on a Modular 1 computer. And most of this system was written by the two Robins, Fairbairns and Walker. And we were then able to run a class using 20 teletypes at once. And here is a shot of a class using these teletypes in the Titan room. Now, this system served us well until Phoenix was at last able to supply us with an adequate online system for extra departmental teaching. And this used teletypes initially, but eventually, VDUs came in, and here are some early VDUs in the Mond computer room. And in the mid-1980s, we went over to using BBC microcomputers, and here is a view of the first room to be equipped with Beebs. Now, notice the plethora of ironmongery surrounding this kit. This is supposed to deter thieves, and notice also that we equipped each station with a dot matrix printer. And the spaces to the right of each of these machines is for the co-processors, which beefed up the Beeb's power sufficiently to enable us to run Fortran programs. And for the first time, there were classes with one computer for each user. And almost coincidentally, this coincided with the end of the television era, so I have TV crossed out. From then on, all instruction took place at the computer itself using carefully written course tutors, and indeed having advice from demonstrators on tap. Well, the BBC computers were eventually superseded by PCs, and they were finally on the PWF, the system which we still use today. Now, in terms of development and innovation, this column suggests that the middle 20 years, roughly 1964 to 1984, were the most interesting. And by chance, at the end of this era, in 1984, I gave a talk in Poland on extra-departmental teaching, and at that talk, I put up this table. And this shows kind of snapshot summaries of the state of play at 4-year intervals over these 20 years. And a number of points stand out. First, the exponential growth in the number of students attending courses was slowing down as early as 1976, but these figures represent the extra-departmental teaching given by the teaching and research side of the department, and by 1976 a good deal of such teaching was being undertaken by the computing service. Now it's interesting to note that the enormous gain provided by the cafeteria system, reducing the turnaround from 2 hours to 5 minutes. And this is an interesting example of an innovation which had nothing to do with technology, but was derived solely from a change in management policy. Actually letting users feed in their own cards and collect their own output was revolutionary thinking. Except, of course, that it was much the way that users had been let loose on EDSAC 25 years previously. Well, so far I've only hinted at what was actually taught. These days the teaching committee plans 70 courses a year, and I don't have time even to give an overview of those courses. But what I have done is to list the main procedural programming languages that our in-house students have been exposed to over the years. Now, until the advent of Hartley autocode, the only practical way of writing programs was to use assembler language. And without David Wheeler, programming would be largely a matter of writing noughts and ones. Autocode did actually survive to the Titan era, but for most of the time of Titan, the main language used on the diploma course was Fortran. The IBM mainframe brought with it good news and bad. The good news was in the form of Algol W. The bad news, of course, was that we were no longer able to use an online system, and all Algol W teaching was via punched cards. Now, since then, we've fallen into a pattern of changing language at 6-year intervals. We've followed with Pascal, Modular 2, Modular 3, and for the past 2 years, Java. And on the basis of linearity, it rather looks as though Java has another 4 years to run. Well, let's now see what was happening on the extra-departmental front in the way of language taught. And for the first half, the pattern is exactly the same. There simply wasn't much choice. And by the time Fortran was well established, the majority of the extra-departmental clients were natural scientists who became quite unnaturally attached to this language. When Algol W became available, I explained to the Natural Sciences Tripos Committee that this was an improvement over Fortran, and I offered to teach it instead. The committee didn't take long to reply. No, thank you, they said firmly, Fortran is the language for us. So for 6 more years, Fortran was continued, and then I offered to teach Pascal. The Natural Sciences Tripos Committee again insisted that Fortran was the only language for them, so another 6 years went by. And I offered to teach from Modular 2. And this time they said, why do you keep pestering us? When you know full well that God intended natural scientists to write in Fortran. Well, by now you must be getting the hang of this story. Another 6 years of Fortran. Fortran went by, and then I offered them Modular 3. I wasn't put off by the rebuff, but of course they said, no, thank you, we still want to be taught Fortran. So then a miracle happened. Quite out of the blue, I received a letter from a physicist, the essence of which was, why are you still teaching boring old Fortran? Don't you know that the world has moved on? Now, there were all kinds of things I could have said in reply to this, but my diplomatic skills were up to this test. Well, I said, I can't imagine why I never thought of teaching anything else, but it sounds as though you have an interesting proposal up your sleeve. How about discussing it? And the upshot was that Fortran at last came to the end, and I outlined a course which aimed to teach various computing techniques using spreadsheets, and almost inevitably this means a course based on Excel. Well, my final thread is about examinations, and I thought it would be of interest to have a look at the very first diploma papers which were taken in 1954. And here I express my thanks to the keeper of the university archive for supplying me with copies. Now, in 1954, the diploma was referred to as the Diploma in Numerical Analysis and Automatic Computing, and there were 2 papers, paper 1 on numerical analysis and paper 2 on automatic computing, with paper 2 having some emphasis on hardware issues. Now, to a 1999 diploma candidate, the numerical analysis paper would be utterly intractable. Despite attending 2 courses on numerical analysis since last October, there is not a single question in the 1954 paper 1 that they could remotely attempt. Now, by contrast, subject to a few minor changes in wording, they could readily attempt several questions in paper 2. It's just that the expected answers would be rather different. Now, here is a sample question from the very first paper 1. Describe the derivation of modified differences. Consider fully the case where delta to the 4th is thrown back into delta squared, and discuss the field of application of the resultant formula. Now, I spent an enjoyable half hour discussing the paper 1 questions with Mike O'Donohoe, who gives the numerical analysis lectures today, and he commented that the techniques implicit in the 1954 questions were really designed for desktop calculators at the time and not really for high-speed computers, hence the way these would be difficult for the modern candidates to take. Well, moving on now to a sample question from paper 2, here is the beginning of one of the paper 2 questions, starting, give an account of the application of Boolean algebra to the design of switching circuits. Now, with a couple of minor adjustments, this would be a perfectly satisfactory question today. Today's candidate would be slightly puzzled by the use of the term switching circuits, but would be perfectly happy with logic circuits or digital circuits instead. Now, you should note in this question that the examiners set a very useful precedent which has been enthusiastically followed by every examiner since, which is to include a mistake in the question. Hands up anyone who spotted it. Ah, a few, yes, goody, goody. You see, it refers to a binary number x, and then a couple of lines later, that same number is referred to its n. It happens that I am this year's chairman of examiners, and I handed in the papers for printing just yesterday, and it would certainly be tempting providence for me to criticize my 1954 predecessor. So it's probably best if I let you, if I say no more on this subject, lest I give you a sneak preview of some of this year's questions. You are, of course, all invited to read them when they appear on the laboratory's webpage on the 3rd of June. I think it is time to bring this history lesson to a close. Thank you.
Our next speaker is Dr. Stuart Lang. He was involved in the laboratory's major graphics work, which has already been mentioned this morning, from 1970 onwards. He then went off in what we regard as the approved laboratory style to develop a company. He returned, having made his pile in California, to research on more modern graphics. We're very happy to have him with us because he still maintains a link with industry as well as doing the research in the laboratory. Stuart Lang.
Slight comments on my business career. When I came here as I came here as a diploma student in 1970, and I then did a PhD with Neil Wiseman, and I left in 75 with no intention of ever returning to Cambridge. Not in a negative sense. I don't think I'd blotted my copybook, but I had other things to do, and I wound up, just to show you how Cambridge leads to many roads, I wound up building COBOL compilers. I had to ask how to spell COBOL. That's my saving grace. I'm afraid it's been downhill ever since. However, it is a point of record. In fact, there are various people here who I'll talk to, but many of the COBOL compilers in the world, in use in the world today, emanate from this area, from this laboratory. So we have our sins as well as our virtues. I came back here in 1990 as a visitor, and one way or another, I've never left. And I'm now a chief executive of a company called ASD Systems, based here in Cambridge, doing R&D on new displays. Right. Let's move on. We have a finite number of time. It was suggested that I look back at the graphics in the lab, which I was most familiar with, which is really the period 1970 to 1975. And I'm sure if we went back to Frank's chart, it would be a proper name for it, but I can't really think of it other than the graphics period. It's the turnover of Titan to Phoenix. And if I was, my very first computer that I ever programmed was a CDC 6600 in CERN. And I was then in Manchester, and I should actually like to pay tribute to the various people from Manchester who are here today, and also to my first professor, looking to my second professor. My first professor was Professor Frederick Williams in Manchester. I've been very fortunate in having two marvellous heads of a department over the years. But my very first real computer, in my eyes, was the PDP-7, which I'm going to talk about. And the reason was, it was the first computer that I could turn off and turn on. And prior to that, I think I may have, in fact, fried a few consoles, but I'd never purposely turned it off and turned it on. That was really the background. Right, I'm going to talk about some graphics. I'm going to talk about current research which I've been involved in, and then I'm going to talk a little bit about, or it's been suggested I talk a little bit about the future. Given the discussion last night about philosophers and hostages to fortune, I'm not going to say very much before I get into that. Right. First thing to go back to is what was wrong, or what was good, or what was bad about the graphic systems there. And I'm going to do one slide in a minute, which is computer sciencey, and the rest of it, I hope, is lower level. Up to about 1965-ish, the whole environment was paper. Everything that was done in computer science involved paper. At a broad level, if a user had to see it, it had to go in on paper and it had to come out on paper. And really the world has changed since 1965 up to now, 1999. We've gone from hard copy, things that you can actually touch and had to touch, to things that you see, and for that matter have to see. And the paradigm, the whole concept of what computers are about has changed. I left in 1975, and actually the first glass teletype came in just at that point. But from 1965 to 1975, the environment, the graphics machines we had here were the ones that I used and various other people's used. But they were, and the most important about them is they were what we called calligraphic displays. And the difference between calligraphic and raster is actually in that picture, and it's put up for a purpose. There is text on there, and there is a raster picture. And the text, you should know about, is easy, well, relatively easy to do on calligraphic display. It's a section of lines and curves, and it's calligraphic displays are very good for doing function plots, circuit diagrams, sort of thing you would do with a pen. And if we used 5,000 bytes of memory to do our pictures, we were doing pretty well, and we'll come back to memory in a moment. To do the other half of that previous picture, which was a real picture, a TV-type picture, was completely impossible when we started. 1970 is when I started. And really, the first raster scan displays didn't come in until about 1980, which is, in fact, after I'd left. So I'm really talking, in Frank's terms, probably prehistory. I'm talking about time when we didn't have memory. 1 megabyte for a picture was just inconceivable throughout this period. So please keep that in context. Right, first displays in the lab. There are 3 displays I'm going to talk about which cover this period, 65 to 75. The 340, which has already been touched upon, which started the research in the lab. The Vector General, which was connected to a PDP-11, and then the laser scan, HRD1. The lab's component, it's important to remember this, this was the transition, these 3 machines were the transition to the first real lab machine that was bought out of a box, plugged in as described yesterday, and worked. Every machine prior to that, the lab had built in one form or another and had then added software to it. These machines actually relatively much worked out of the box, and software was the lab's element, not the hardware. The initial justification was CAD. We went on and did a lot of compiler work, which is where I did a lot, with Martin Richards, who's somewhere in here, there, and operating systems. And for those of you who want to add to the history lesson, when we started this, Unix wasn't invented, and Microsoft was not even conceived of. Right. Let's go to the PDP-7. Simple little thing. It had 1024 by 1024, which is about a megabit, a mega resolution. That's 1 million points that you could paint on the screen. But actually, it only had about 18K bytes of memory, 8K words at 18 bits. It was a calligraphic display. So the ability to actually write a picture of 1024 by 1024 was just impossible. You could draw things on it, and that was it. It was about a 13-inch screen. It was a monochrome green, had a light pen interface, and perhaps its saving grace was it had a link to Titan, where we could keep files and run assemblers, and to a certain extent, at one point, run the compilers. I think the point about the PDP-7, it was a very happy machine. I know that's a strange thing to say, but for those of us who used it, and I used it a little bit, really in the diploma course, it was the machine in which a lot of people, and not actually I, produced games, and the one that we all know about, of course, is the Game of Life, John Conway's Game of Life, cellular automata. But it also did things like chess and other such. But let's start. This was actually, I don't think many people need to be told what this is. There's a screen, there's a keyboard, and there was a system console, a teletype. There's also Neil Wiseman there, who I should pay tribute to this point. Neil was my supervisor, and he died about 4 years ago. He was a wonderful person, and in the course of his time produced some 40-odd PhD students. And much of this graphics, I believe, wouldn't have happened without him. The other major players were Charles Lang and the group doing CAD. Neil's group was more electrical CAD and a certain amount of typesetting, University Press, and word processing. I should just, for those of you who don't recognize it, this is the, well, I should point out the machine first, but for the interested, this is Chris Cheney as a young lad. And I have not asked him, but I'm quite certain it wasn't an early karaoke machine. It was, has probably some more absolute use. And actually, and the second question, I do not know where this picture was taken, but this machine in its time was in what is now, in this new building, was in the, what's called the discussion room, which is the back of the Bobcat room. But I suspect this was taken in the earlier building. You can see the environment there. Paper tape in, paper tape out, a screen, a sign that's not very well visible, essentially talking about secure systems. Before you turn the machine on or off, tell the Titan operators. I won't record what happened if you didn't tell them. It wasn't the machine effect, it was the human effect. That was a very lovely machine, and it worked well. Let's step on to the Vector General. This was driven by PDP-1145, and it was 4096 by 4096 resolvable points on the screen, which is, if you do the sum, 16 mega points. An enormous address space for a screen. And in a machine of 48 kilobytes, you can see we had some problems filling the screen. It's a calligraphic display again, and it was a 19-inch screen, light pen. And there are other hardware features like matrix transformation. Interesting point deep down is the actual memory change. We went from 18 kilobytes on the 7 to 48 kilobytes on the PDP-11. And I did my back of the envelope arithmetic, and it's about Moore's law change. It's just under 4, factor of 4, and it was about 6 years difference. So even prior to Intel, Moore's law operated, which is quite good. See the machine. I should apologize. This picture was taken in, I guess, 1975, and it's been suggested that two heads are better than one, but but that is not the true reason. The true reason is I moved at the wrong time, and that's yours truly. Mechanical points, it's worth showing. There's the CPU on the right over there with the lights on. That's where the processor was. An exchangeable disk above my head, and a screen, a very lovely 19-inch screen. System console was at that point was a Data Dynamics. Originally it was a digital machine. I seem to remember it failed, that's why it got replaced. Oh yes, Frank reminded me, because he stood there earlier in the speech and produced his paper tape, show all of us his original program. Well, I should just say one little thing about Frank's very good memory wherever he's sitting. I came back, this was done in 75, and I came back in 1990, having spent 15 years building compilers and being involved in COBOL programs that, you know, 1 million lines is a small program, and there's usually 2 or 3 copies of it. I came back and I was at a lunch, having a bread and cheese lunch, and Frank came up to me and said, "Do you remember that bell ringing program you wrote in 1974? I've just re-edited it or recompiled it to run something, and my brain was, I have to have it to Frank, I'd completely forgotten we ever wrote a bell ringing program. And, but this is the machine in which we do it, so Frank, your memory is better than mine." Let's just go on to see the screen, because the calligraphic stuff is worth knowing about. This is a full screen. It's a BCPL program, and the thing to perhaps notice is the scanning of the photograph in, because this was taken with a 35mm camera, has produced all the artifacts you see there are not the artifacts that the screen had. They've been introduced by scanning it in. A nice screen, and I won't go into the software to drive it. These 2 fingers were an early version. This is 72 probably, and it was originally Neil's idea. The 2 fingers were actually selecting a block of text like you would do with a mouse now, and just select it with a button. But I think I'm quite sure Xerox PARC was probably parallel with this, so I wouldn't claim originality. More of the screen, just things you could do. I showed this, I put up particularly just to show you the character set, things like symbol and alpha and beta, all built in the hardware. Didn't take any memory space. We just put a single 8-bit ASCII character and up it came. And hardware rotation, entirely in the hardware. This rotation on the right, the symbol, simply told the hardware of the vector general to rotate it when it displayed it. It was a very lovely machine. Go on with a few more of the photographs. This is Neil explaining to actually Ian Braid, who I think is somewhere here today, the typesetting which Neil was doing with the University Press. And behind Neil is a printer for the HRD1. That white, talking about mistakes management, that white table is still around the lab. We've afraid the contents have gone. And this gentleman you may recognize is Peter Robinson before he went for the wide parting. Right, enough, we have to keep going. Laser scan. This, I have to pay tribute to the people who built this, which was Otto Frisch, Graham Street, and Peter Woodsford, who are still probably somewhere with us today, I think. Peter, I think, is here. This machine had an addressability of 50,000 by 35,000 points. And I do not know of a display today, 25 years on, that even begins to match this. It was a storage display, calligraphic storage display, 50-inch screen. It had a film which was written to by a laser and a back projector which projected the film onto the screen. It took about 2 minutes to get anything really big up there. But actually, if you're putting up this sort of size, you're not particularly bothered, at least I wasn't. The actual visible resolution, that's line resolution, optical resolution, was still very substantial, and it was only diffraction limited. Vast amount of software written for this, Geno particularly, which stands for graphical input-output. which was produced in the lab, and Peter was one of the major drivers for that. Just so you know, the background is it's spun out from bubble chamber work, which was done originally in the basement of Austin building. I could go on about them. LaserScan still exists. It was the first company on the Science Park, and the machine was used in mapping applications and banknotes for a long time. This is the machine, 50-inch diagonal, driven off a PDP-11. I'm pretty certain that room is actually at LaserScan. I should say the Vector General room is up where the machine and the PDP-11 were up in the, and this, when it was in the lab, is in the room that is now the Hitachi room upstairs. Point about it, I said it was a film written to by a laser, and it's worth recording that the interesting danger was that when you opened it up to put the film in, which you could occasionally change, you've sometimes found the laser beam warming your tummy. I don't know if anybody actually got burnt, but I do know that we all had to go and get our eyeballs photographed. I know John Dowland photographs eyeballs, but we had to have our retinas photographed before we were allowed to use this. Another picture, very classical mathematical function. Yet another one, a map, and I don't know where that map is. And finally, you could not only could you print to the film and have it projected, you could print to a separate film. This is the sort of thing you could put up on a 50-inch screen, so if you wanted a little debugging, you could get 18 pages of output, which, at a time, I never had time to write a really good debugger for it, but it was quite something. And just so it's there, this is a blow-up of one of those pages, and again, these are all scanned in, and all the errors you see on there are scanning errors. They're not, they're raster scanning errors, they're not calligraphic errors. Right. We should get into current display work. I've been involved in auto-stereo display, which I'll talk to you about, and really it started in engineering, and it's still going on in outside and inside, commercially and inside with research. There's an awful lot of other work going on in the lab, which I'm not going to talk about. It's good, but I'm not here. Simple physics. If you look at a block, a set of blocks, we're trying to produce an effect that if you looked into a space which has got 3 blocks in it, a set of objects, you will see a 3-dimensional image because you've got 2 eyes. Well, if we do the thought experiment, second piece of computer science, thought experiment, all you have to do is divide up the space in which you see this into solid views, so that if you move your head within those slits, it'll stay constant. We just need some physics to replace those slits with cameras and a display, and you will get 3-dimensional pictures. If you move your head will fall into the different slits, and as long as those slits are half the average distance between your eyes, then you will continue to see 3D. You'll see 3D all over that space. How do we implement it? Well, Adrian Travis in engineering had the idea. Essentially, a bank of light sources, a lens, and a space out here. If I trace the optics, if you turn this light on with the lens, you'll be able to see that light there. And if you were to turn this light on, you would see it here, and so on. Well, if you do it fast enough, and in sequence, so these lamps here, and you actually put a screen in here, then you will see different views from here. The only problem is, of course, we haven't got a liquid crystal lens that will go fast, a liquid crystal screen that will go fast enough. But we have got cathode ray tubes. So if you do the transformation, which I won't take you through, optically you can replace the liquid crystal screen by a cathode ray tube, use a liquid crystal shutter instead of a bank of lights, and look in through the collating lens. The observer is somewhere out here. You will see the screen in 3 dimensions. Sounds crazy, it works. The first machine we built was in the early 80s. By 92 we had a machine that properly worked. There's a triumphant team there with John Moore, who's probably the best engineer, the best analog engineer around at the moment, behind the camera as ever. This machine had 7 views, 7 areas you could put your eyes in, and 320 by 240 resolution. Not very big, 10-inch screen. It's that blue, these pointers tend to be a nuisance. It's this thing here that you look into. The picture is very carefully taken because the depth of that machine is about 1 meter. However, it's good enough to demonstrate the principles. Moving on, we've been building now, we then went through a cycle of commercializing this and working with outside companies. And we built a 25-inch diagonal screen, which you actually can see there. And as you may guess, and as I alluded to earlier, most of the graphics applications that people really want are games. And the people who are prepared to put up money for this come from the games world, so they explains the body shape of that. I won't go through most of those. There's one other person from the lab. There's Dave Garnett, who many of you will remember that's there. The others they are not lab people, so we'll leave those one side. The optics path, just so you can see it. There's a bunch of CRTs facing down here, lenses about here, and then a mirror to flop it up to a Fresnel lens here, and then there's a mirror to drop it out to there. I don't show the computers. It actually uses, that particular one uses 4 digital alphas. I think they're 350 megahertz. That works and is out doing aerospace work. There's a large aerospace company. The other people who've got money are aerospace still. They're in California. So that worked. So we then went on and built a 50-inch one. This is the point where people begin to think we're a bit crazy. This is a 50-inch screen, and we just used crude mechanical optics and dichroics to put this together. There is, and I think the best thing to do is to say, if you look at this area, I'll show you a photograph of it in a minute, but essentially there is a red tube, a blue tube, and a green tube being combined. There's an awful lot of physics which I can, and I'd be happily afterwards tell you about. We haven't got time, like light loss and energy efficiency of this. These displays are made out of projection tubes. Here is the 50-inch one, which worked a little over a month ago here in Cambridge and has now regrettably gone out to Tokyo, which is where it's going to earn its keep. It's got 2 viewers. Each viewer sees a 50-inch screen, and each viewer has got an eye box of about 30 centimeters wide, in which there are 15 separate views. So it takes a total of 2 lots of 15 video channels into the electronics which aren't shown. So it's 30 video channels going into this. The cabling is simply video input to it. And if we take the covers off, that's what it really looks like. It's not very clear in this photograph, I'm afraid, but I will. The combining, which I'm about to show you, is done in here. There is, it's too dark properly to make it out, but there's a blue tube here, a green tube here, and a red tube here, and they're combined in there. And then it comes up through the lensing, through the mirrors to come out. The diagonal on those lenses is about 14 inches, just shy of 30 centimeters. I think it's probably one of the largest lens systems that's been built that way. And what does it actually look like? It's Granny. That's our sort of standard piece of software. Some people have asked if I can show the autostereo on this screen, and I assure them it's not very possible. But then if you've been following, I'm sure you wouldn't have asked the question. Right, enough of autostereo. We have a few minutes left. We've been asked to say something about future displays. Well, first of all, taking the philosopher's view, I'm not going to be hostage to fortune. There are 2 things people really ask for. They always want it brighter. I've yet to meet anybody who's asked for a display that is less bright than the one that they've had in front of them. And the second thing is they want to make it probably less fragile, more reliable in some sense. The other things are just physical size, smaller, bigger, or lighter. That depends which mark you're at. 2 things about smaller. I'll just give some examples of things that we don't normally think about, perhaps. you are about to get in high volume, very, very cheap displays, which are a CMOS-backed chip, a little piece of liquid crystal and a piece of glass on top of it. They are already coming out in consumer devices, and they will come out in very high volume if somebody can find an application for it. The usual story. Second point, which is worth doing, people asked about lighter displays. Well, I'll just make the point about lighter displays. Actually, system integration is the issue. This is the classic. Most people think of lighter displays, laptops and things like this. This example has been put up by, in fact, by the US Navy. If you can save 1,377 pounds, they would like to hear from you, because it's 6 people in an aircraft that is in operation. Lighter means different things to different people. Beware of that. And the other thing is bigger displays. I would like a wall-size office display, but nobody has yet produced one that's suitable for perhaps my use and maybe for your use. But I'll just show you ones. We know it's possible. The HRD1 was a brilliant machine over 25 years ago. We can't buy one now. There's obviously a market element there. So finally, we should wind up, done something on earlier displays, or stereo displays, and future displays. Basically, soft copy has changed our world from when I started. Question perhaps for the next generation is what next? And the answer is we are missing something, and I don't know what it is. But the transformation from hard copy to soft copy has really been driven by semiconductor technology. We've had a gain of something like 256,000 in the power of in the size of memory, the power we can buy today. I can't conceive of that, and I don't think any of us could conceive of it in 1970. But it's quite probable that by 2030 we will have had another increase of 256,000. And I suppose the challenge for the younger element here, who are certainly here, is what today are we now failing to see? Because I'm sure there is something. Right, thank you very much.
Thank you, Stuart. We made all these plans. One of our little plans that went astray was that there would be time for questions. But people give all these fascinating talks, which unfortunately occupy all their slot. So you'll have to nobble the speakers afterwards.